Thank you very much for joining this webinar. My name is Patrick Wolschlegel, and I'm here to give you some information about memory debugging on PSDaint, the CSCS system. So in order to do this, this webinar will be divided into two different parts. The first part will be a small presentation about memory debugging and memory bugs. And once we've gone through the features that are available in Allinea Forge, we will move on to a live demonstration where we'll show you through different examples how to use the memory debugging on PSDaint. If you have any question, feel free to ask these questions in the chat or directly in the microphone so anyone can talk. Just ask your question, feel free to interrupt, and I would be very happy to answer any questions that you would have. So without further ado, I suggest we get started. So when people are writing applications, most of the time they introduce bugs, and there can be a lot of types of bugs that can be very nasty. So depending on the different categories of bug, like for instance, bugs that are very easy to reproduce, or bug that will vanish when you try and start to investigate, or bug that happen randomly and not really sure what's going on. The common point about all this kind of bugs is that they are very often related to the memory. Typically, if you have a bug that doesn't have a deterministic behavior, that will happen sometimes or generate incorrect results or will disappear on a few runs and then come back, there's a very high probability that these bugs are related to the memory. So they are typically very difficult to find, but the good news is that Allinea Forge includes memory debugging features that you can use. And this is where we come in as a company. So as a very quick reminder, we already discussed this on previous webinars. Allinea is a software provider company, and we have two different tools that we make available on the market. The first one is Allinea Forge, which includes debugging and profiling capabilities. The second one is Allinea Performance Report. So the application and the software tool we will focus on today is the one that is available at CSCS, and that is Allinea DDT. So on CSCS systems, you have access to Allinea DDT Supercomputing, up to 65,000 MPI processes. This means that you can pretty much debug almost any kind of job on your system. This license supports MPI, but also GPU debugging, meaning that you can debug applications using CUDA, OpenACC without any problem. You also have access to Allinea Map, which is the profiler. But this is only a trial license, which means that you can only profile the first 30 seconds of your job. Right, so if we look at memory debugging in Allinea DDT, when you start the tool, and we'll see this in a minute in the live demonstration, you land to what we call a run dialog. In this run dialog, you have a menu called memory debugging that you can activate. So there is a little tick box that you can activate, and you also have a detail entry on the right, and if you click on these details, you can find a lot of configuration options in order to make Allinea DDT debug the way you want. All these options are available on the CPU side, but if you look, you can also use this on GPUs. When you activate CUDA debugging or OpenACC debugging, you can also monitor memory bugs happening inside the GPU. And this is done by ticking the appropriate box, like, for instance, track GPU allocations or detect invalid accesses. The whole point of the memory debugging in Allinea DDT is to make sure that bugs that happen randomly or that may be hidden without causing any crash or any failure are detected. So the purpose of the debugger is, in essence, to break your code and make sure it doesn't run to the end, but stops when a memory corruption or a memory error happens. So how is this possible? This is possible thanks to two different mechanisms. The first one is what we call a dmalloc library. So in the directory where Allinea DDT is installed, if you look at the screenshot at the bottom, you have a directory called lib/64, and this directory contains different libraries called dmalloc, and you can see a list like libdmalloc.th, libdmalloc.th, cxx, etc. All these different libraries are very important because if you want to enable memory debugging on your machine, you need to link these libraries to your application. On most systems, this is very easy and this is completely transparent. But on a Cray machine, well, first of all, the best practice is to use statically linked binaries. So for this reason, we cannot use an automatic linking mechanism. But this is easily changed. So if you modify your makefile and add the appropriate line, which is the one that is available here, you will be able to use the memory debugging very easily. Depending on the debugging library that you use, you will also need to change the appropriate entry. So if you're using a C or Fortran code, you have the choice of C or Fortran with a thread-safe or non-thread-safe library. You also have a C++ library, which is thread-safe or non-thread-safe. As a rule of thumb, I would always encourage you to use a thread-safe library, so either C++ with threads or C Fortran with threads. These libraries in your installation directory end with the th keyword. And this will make sure that if your application is using threads, or it can also be control threads, it's not necessarily OpenMP or POSIX threads, then you will not have any problems. So I recommend to use this all the time. So once the memory debugging library is activated, you have three different options. You have three different levels of memory debugging. We have fast memory debugging, balanced, and thorough. Every time you choose one of these level in the memory debugging scale, Allinea DDT will activate different features. And typically these features, you can see them inside the run dialog. You will have the keywords appearing. So obviously I recommend to use just the scale, but if you're an expert, if you know what you're doing, you can use custom keywords and use only the checks that you're interested in. Typically, if I take an example, all of these keywords are described in the user guide, but for instance, let's say that I'm talking about the free blank option. This means that every time you deallocate an array, Allinea DDT will paint the memory with a known value, and that would be typically 0, 0, 0, 0. Why is this useful? This is useful because if you are working in a code and you do a free of your array, without this feature, the previous data is still available in the memory. So if for some reason your application is trying to read this data, it will read the correct value. But this is only happening by chance, and it may happen that another allocation is made and will corrupt the data and your program will fail. So the reason why free blank is important is because if you're doing a read of these values, the fact that the values of this memory have been repainted and have been erased ensures that your program will crash when it reads it. So basically, we make sure to crash your application when you do an illegal access. And all these different features together can be used in order to find hidden bugs that would not necessarily crash your program or that would not necessarily be visible from a user perspective. One aspect that is very important is that depending on the level of memory debugging you use, you will add another head to your application. So if you have a fast memory debugging, the program will run pretty much at full speed, but if you go to a thorough memory debugging, the application runtime can be slowed down by a bit. So most of the time, this overhead is small, but if you're using very complex C++ applications, it can be a bit bigger. One way to reduce this overhead is to change the advanced options available on the memory debugging menu, and typically you can choose different things. First of all, you can check how often you want the heap to be monitored. So it can be every 100 heap operation, meaning every 100 allocation, for instance, but you can increase this number. You can also decides not to store the backtraces for memory allocations. This is useful because it shows when you're looking at the pointer where it was allocated, and by default this is enabled. But if you end up with a very high overhead, unticking this box will most probably ensure that your application is running much more quickly, with memory debugging. And if you want, you can also target the memory debugging to a few processes. For instance, you have different communicators. You know that you have a memory bug on the master processes, which is maybe processes 0 to 3. You do not need to activate the memory debugging for all of these processes. So this is also something that you can configure. These are very advanced options. Most of the time, you will not to change them, but just in case, we give you the option to do so. The second important feature available in Allinea DDT is what we call the guard pages. So guard pages are a very powerful feature. When you create a memory allocation, you can choose to have forbidden red zones before or after the allocation. This means that every time your application reads or writes one of these guard page, the application will stop immediately. And DDT will tell you specifically you have done a memory overflow or underflow. Now, one of the common questions that I see very often is, why can't we have guard pages before and after a memory allocation? And this is what you can see with this picture here. The guard pages are always aligned with the pages in your memory. And this does not necessarily ensure that the memory allocation itself will be aligned with the memory. So typically, if you look at this bit here, let's imagine that I have guard pages before my allocation. I have my memory allocation. If I wanted to do another guard page, it would start on this particular point here. This means that even if you're doing a read or write access in this little gap, nothing would happen. So this is the reason why this feature is not available for both before and after memory allocations. You have to pick one. This means that if you want to make sure your code is safe after allocations, you have to do a one run. If you want to check there is no problem before the allocations, you would need to do another run. So in any case, this feature is extremely powerful because throughout the whole execution, if you're doing a read or write, you will be able to detect it. Now, it does have, there is a trade-off. And the first trade-off is that if you're using Linux, there is a limit in the kernel that allows you to do only up to 32,000 guard pages. For most applications, it is fine, but again, if you have a memory-heavy application, you may reach this limit, in which case you would have an error message called mprotect fails, meaning that you've reached the limit of guard pages you can do. You can change this. It's possible to change it, and I don't think you need root access for that. But just be aware of this. The second thing is that when you're using the guard pages, there is an additional memory usage cost that comes with it. And again, most of the time it's fine, but if your application is already taking almost all the memory of your node, you may have an out of memory error triggered by this feature. Now, the good news is all the memory debugging features in Allinea DDT can be activated at runtime. So if you start an application with a fast memory debugging and no guard page, you can very easily go to a certain stage in the application, for instance, past the pre-processing phase, and activate guard pages, activate additional memory features at this stage. This is good because it ensures that you're not monitoring the memory areas that you know are safe, but you can focus your investigation of bugs on the memory areas that you're most interested in.